Hello. So the purpose of this video is to be kind of an add-on to lesson number 17, linking electricity and magnetism. And that's simply because there's a lot of elements going on in that section that are very visual. It's hard to just have a static diagram or something like that and try to explain it. The first thing that I do want to mention is the difference between the way Americans explain current compared to pretty much everybody else on the planet. And this all kind of goes back to Benjamin Franklin and sort of the way that he imposed this idea on us of positive charges moving. So if I was to draw a diagram of an electrical circuit like this, the positive terminal is the longer one and the shorter terminal is the negative one. Now, if you're thinking like Ben Franklin and you're saying positive charges are the things that are moving around, that's his single fluid theory, you would talk about positive protons wanting to move away from the positive terminal and being attracted to the negative. So the positive protons would move that direction. The name that we give that is conventional current. And it's named that only because in America, they see that as just the standard. It's convention. So it's a little bit kind of weird that way. But the rest of the planet, and even if you held down an American physicist and gave him noogies on the head and said, but is it really protons moving? They would admit to you, no, it isn't. So they know that in fact, it's electrons that are moving-ish, because it's not even totally electrons zipping through these wires individually, but it's more kind of this domino effect sort of thing going on. But still, in general, negative electrons are moving repelled by the negative going towards the positive. The name for this is electron flow current. And it is sort of, in terms of models that we can use, it's the best model we've got that explains basically what's going on. In everything that we're going to do, we always assume that it's negative electron flow current, unless we've got a good idea to think otherwise. The other thing that this does mean, though, is that whichever system you're using, you do basically get an equivalent result. Because whether you talked about protons moving in this diagram counterclockwise or electrons moving clockwise, you would actually come up with the same result. Because they're the same amount of elementary charge, and moving in opposite directions, positive and negative, you would get the same sort of overall effect. But we are going to assume negative electron flow current in everything that we do. And that means that when we're doing the majority of our diagrams and stuff, we're going to be using our left hand, because left hand is anything negative, whether that's electron flow current or whatever. If we have to do anything with protons, alpha particles, conventional current, anything positive, we switch to our right hand. So left hand for electron flow, right hand for anything positive. Basically, that's the convention we're going with. Now, there were also all of those symbols that I showed in the notes about, like arrows pointing different directions and things like that. We're going to be using those in our diagrams now as well. So you have to be prepared to use them. Now, the first rule that we're using, the first hand rule, is kind of the most fundamental basic one. It's the one that indirectly Oersted was using when he did his original demonstration. And the thing that I always want you to remember is first hand rule. It's when you say that, when you show it with your finger, it's like you're saying, I've got a straight length of wire. And that's what you have to be imagining, is that the first hand rule is all about what would a single straight piece of wire do if it's got current flowing through it. As the current flows through that wire, it induces a magnetic field that surrounds the entire wire. So at its most simplistic, I could draw a diagram like this, and I could say, look, there's the current flowing up the wire. Now, I could put an E with a minus sign there to represent electron flow current. I can also put the letter I to represent current. Either way, as long as I'm doing something that indicates the direction of the current flow in that wire, it would basically mean that in this wire, I've got current going upwards. Now, in the first hand rule, you have to grasp the wire with your hand, and in this case, since it's electron flow, I'm using my left hand. You grasp it with your thumb pointing in the direction that the current is flowing in the wire, and your fingers wrap around in the direction of the magnetic field. Now you got to be careful in that part, because your fingers don't just stop. Your fingers wrap around. And that's what we have to visualize about the magnetic field, is it doesn't end in one particular spot. It wraps around again and again and again, just continuously in a big circle around. Now, one thing that'll help you with these diagrams is, instead of trying to imagine it on the page, is to have something with you can grab. And I'd suggest like a water bottle or something like that, something visual that lets you see it. So I'm saying that this wire is like the water bottle, like this. And so I need to grab this with my left hand so that my thumb is pointing up in the direction of the current. So doing it like this would be wrong, because my thumb is pointing down. I have to reverse my hand and point it like that. Now I've got my thumb pointing up in the direction of the current. You can see my fingers. Now this is where that whole wrapping around thing comes into play. Do you notice how if I'm in front of the water bottle, my fingertips in front of the water bottle, my fingertips are pointing off that way. So what I could draw on here is a circle with the line erased, because if I was putting a compass in front of the wire, you wouldn't be able to see the wire, right? So that's my compass. And the arrow would point that way. And I can label it as B for magnetic field and say, look, the magnetic field is pointing that way in front of the wire, because the direction a compass would point is the direction of the magnetic field. As my fingers come around, oh, and also, it doesn't matter where I position this along the wire, because anywhere in front of the wire, the magnetic field will be pointing that way. Okay, so I just happen to draw the circle there. But the important part is it's in front of the wire. As my fingers continue to curl around, by the time my fingertips get to this side of the bottle, my fingertips are now pointing away from us, like into the board. So I'm going to draw a circle here, and I'm going to draw an X, label it as B for magnetic field, saying that that's where the magnetic field is going away from us. And again, I could draw that circle anywhere on this side of the wire, and it would represent that sort of a direction. Now this is the part where you gotta trust me a little bit, but if you're also kind of following along, you should get this as well, I hope. As my fingers wrap around, my fingertips are now behind here. And as my fingertips come around behind, they're pointing off this way. So pointing that way. So what I'm gonna do is I'm going to draw, and just to, kind of keep it consistently same sort of region here, I'm just going to draw the circle there. Notice I can still see the wire, because if I place the compass back here behind the wire, you would still see the wire, right? And it's here that the magnetic field is pointing that way. Finally, as my fingertips come wrapping around to here on this side, my fingertips are pointing out towards the camera, out towards you, away from the board. So if I'm on this side of the wire over here, circle with a dot labeled as B. That's a lot of compasses, but it's this idea of wrapping around. Now, there is also a really old video of me that's available from when my classroom was actually still at the front of the school, where I show compass needles all pointing in the same direction. And I'd suggest you watch that video, because it does give, again, sort of a different 3D-ish way of looking at this, with me being the wire and all these compasses placed around me. It might help you a little bit with this in front, behind, all that sort of stuff. Now, in this diagram, what I had done is I had said, here's the direction of the current. Ask me, like, where is the magnetic field at different points? What I could also do is give you a question where, okay, let's say we drew the wire like this, and I said to you, in this situation, I placed a compass, make that look a little bit more like a circle for you, like that. And I'm going to tell you that here, the magnetic field was coming out of the board towards us. And I want to know what direction the current's flowing in the wire, because with the hand rules, it's always going to be one thing that we're asking you about. Whatever, hand rule we're using, we give you all the information about something, and then we ask about one thing. So in this case, I'm giving the magnetic field, and I'm asking what direction is the current flowing. So for this one, if I grabbed the water bottle, again, is supposed to be my wire. I should get some product placement or something like here, some funding from Vitamin Water for this, I think. But if I grab it like this, and I look at where my fingers are on top, not behind or below or in front or anything like that, but as my fingertips wrapped on top of the wire, do you notice my fingertips are pointing away from you? That's not what they're supposed to do here, because the magnetic field is supposed to point out above. So that means I've got my hand backwards. Take your hand, wrap it like this. Now you can see my fingertips above the wire, above, are pointing out towards you. And my thumb is going that way. So that means that in this wire, the current would have to be pointing that way. And I label it as I and say, oh yeah, that's great. What if the question had said to me, what direction is the current, if it was conventional current I was asking about? I would have used my right hand, and I would still grasp it so that my fingertips above are pointing out towards you, because that's the fingertips are the direction of the magnetic field that's being induced around the wire. My thumb is pointing that way, because I'm using my right hand. So if I was doing this, I would have labeled the direction of the current that way. And I would label it as I-C-O-N-V to point out that it was a special direction of the current. It was conventional current that I was doing. Either way, whether you're doing regular current or conventional current, you can get the correct answer. It's just that most of the time, this is the one that we're asking for, okay? But sometimes, even if things are labeled that way, it could happen. That's just what we have to go with. So that's the first-hand rule. And I like the first-hand rule. It's a good one, but we honestly don't use it as often. And you know what? There's actually been some great questions, diploma questions over the years where they did, but it's not as common. The second and third-hand rules are probably the ones that are a bit more important to us. So, second-hand rule. Second should sound like the word solenoid to you. And you say, well, what's a solenoid? Solenoid is basically where, and I'm just drawing this as a reference, okay, so imagine this as being any cylinder, like the water bottle. It's just a reference for you to see the wire I'm about to draw, because this is supposed to look a little bit kind of 3D-ish. I tell you that I take a wire, and instead of it being a straight wire, it is wrapped around, wrapped around, wrapped around, wrapped around. The idea is, like, if I took this and I was wrapping this wire the same way, I would have started down here at this end, and I'm wrapping around like that, okay? That's what that's supposed to look like. A solenoid technically is, like, this could be a toilet paper tube, although I don't know where you're finding toilet paper, but this could be a toilet paper tube, it could be a water bottle, it could be your arm, I don't care. Wrapped with wire around it, it actually magnifies the magnetic field that's induced by the wire greatly. It's because it's kind of like focusing it with all these layers of wire together, right? We just have to make sure the wire is always wrapping the same direction. Technically speaking, if you replace this cylinder in the middle with a ferromagnetic material like iron, so like a nail or a bolt or something like that, what you've technically made now is an electromagnet, because by making this magnetic field through the wire, it'll align the domains that are inside the ferromagnetic material, and the magnetic field exponentially jumps up to a much higher point. That's why it's actually relatively easy to make an electromagnet that's quite strong with some pretty wimpy materials. As long as you've got a ferromagnetic core with wire wrapped around it, and then you connect it to like a battery, you will have an electromagnet. So in this case, now that we're on the second-hand rule for solenoids, things do kind of change around a little bit. Now in our second-hand rule, because it's the wire that's curling, your fingers have to wrap in the direction of the current in the wire, and your thumb points to the north pole that's induced in this solenoid. So let's say in this wire, I had the electron flow current going up in front, and then it has to wrap around down behind. So here's my water bottle again, and I imagine that the wire has current coming up in front, and then my fingers grasp it, wrapping around behind. My thumb points off that way. And again, I'm using my left hand, okay? Left hand for electron flow. Thumb pointing this way means that on the solenoid, this will be north, makes this end south. Basically, it acts like a bar magnet. In every way that's measurable, this is now a bar magnet, okay? And so even if you want to draw electric or magnetic field lines, they would come off of the north and go into the south, and off of the north and go into the south like that. And technically speaking, they don't end. The magnetic field lines kind of continue through inside the solenoid as well. But they do this kind of unending wrapping around sort of thing as they go through. Most of the time we're really focused on what's happening to the magnetic field outside. But if this is a hollow tube, for example, the magnetic field would actually continue inside as well. So it's kind of a little bit freaky that way. But remember, second hand rule, fingers wrap in the direction of the current, thumb points to the end of the solenoid that's north. One thing also to point out is if you're ever doing any of these hand rules and you feel like you have to be like double jointed spinning your hand around or something, no, you never have to hurt yourself doing the hand rules. Instead, do some simple things like turn the whole diagram like this or something, because just that simple act of flipping it around is probably enough for you to make things a lot less painful. But you should never ever have to hurt your arm or something by twisting around too much to do the hand rules. So just like with the first hand rule, here I had shown you the current and I was asking for the direction of the magnetic field. I could tell you something about the magnetic field and then ask you for the current. So I'm going to draw my sort of representation of, the tube thing like that. I'm going to tell you that the wire is wrapping around like that. I'm going to ask for the current, and what I'm going to tell you is that I placed a compass, let's say here, and the compass indicating the magnetic field at that point was pointing that way. So I've got to think, a lot of times people try to run to the current and stuff. No, no, no. First, let's figure out things about our solenoid, because if the compass is pointing like that, I've got to think, what pole would be here that would actually make the south end of my compass, because that's really what these arrows are. This part right here is south. What would make it attract to that south if this was north? Because north, a little south north there, north and south would be attracted, right? That makes this end south. So that means that when I grab this as my solenoid that I'm looking at, I've got to make sure that my hand doesn't point this way with my thumb pointing down, because my thumb has to point to the north end of the solenoid. So I'm going to grab like this, thumb pointing to the north end of the solenoid. And if you look, as my fingers wrap around, as my fingers come in front, do you notice how they were pointing off that way? Okay, so that means that in front, the current is going that way. Now, sometimes people are worried about this kind of diagonal sort of nature to it and stuff. Don't worry about that. We're drawing that just to kind of offset them a bit so you can see this wrapping around thing. In general, the current is going that way then. The current is coming this way in front. That would mean that it would wrap around behind. And don't draw these arrows in 17 places all along the wire. One arrow, done, leave it simple. Okay, that's usually the best way to look at these. Okay, so first hand rule, straight piece of wire. Second hand rule, a coil of wire around some sort of a core, maybe even, that sort of an idea. And then there's the third hand rule. Third hand rule is probably the most helpful one for us. It's the one that lets us do the most stuff. third hand rule has 3 parts. Because basically what we're looking at is one of 2 possible situations that's happening. Either we've put a wire in an external magnetic field and we want to see how it's getting pushed around, or we're shooting charged particles through an external magnetic field. And again, we want to see how they're being pushed around. So let me show you an example of one of the ones with a wire, and then I'll show you how the parts of the hand work with it. So I tell you that I have an external magnetic field. Now, like we've done before, I know the rest of the magnets are out here and stuff. These aren't monopoles or something, but all I'm really concerned about really is the magnetic field that's happening in this region right between the poles of the magnet. So I've got a magnetic field that, if that's all I was asking for, just for now, that's all I'm asking for, what's the direction of the magnetic field between these poles? Magnetic fields always point in the direction that a compass needle would point, so the magnetic field is pointing like that. And I'm going to call this B external, because it's the external magnetic field being created by this magnet. It has nothing to do with the magnetic field that the wire itself is creating, because that's like first hand rule. But where's the wire, you ask? Well, the wire, I'm going to draw like this, and I'm going to tell you that the wire has current flowing. I'm going to do it this way. I'm going to say current flowing down. Now, see, the wacky part is, as soon as current's going through that wire, it induces its own magnetic field. That magnetic field has to push around somehow with the external magnet's magnetic field, but what's that going to do to it? Is there going to be a push, a pull? Like, what direction is it going to be? In the third hand rule, your thumb is the direction of the current flowing in the wire, or the direction that the charged particle is moving. Your fingers point in the direction of the external magnetic field, and your palm is the direction of basically the magnetic force that's pushing on, in this case, the wire. So if I was going to do this one, I'm going to shift over a little bit here, because it'll be a little bit easier for my hand this way. I've got to take my hand, and I'm going to do the external magnetic field first, because I find usually that's easier for me to do. My fingers are going to point this way. Now notice, it's only the fingers I'm talking about. My fingers, even if I start rotating my hand like this, my fingers are still pointing in the direction of the external magnetic field from north to south. I can rotate my hand like this, but I can't do anything like this, because then my fingers are screwed up, okay? So fingers pointing in the direction of the external magnetic field. Now the current in the wire is pointing down, so I rotate my hand so that my thumb is pointing down in the direction of the current. Fingers are still pointing in the direction of the external field. That means my palm is like, if I was pushing with it, I'd be pushing into the board. So I'm going to label that as the direction of the force. Away from us, circle with an X, FM. Sorry, I don't have any other colors than blue and black. But that FM, that's showing that for any part of the wire, just the part of the wire that's actually in the field, it's going to be pushed away from us. That's the third hand rule. Now, what happens if that wire, and I'm just going to have to erase a little bit here, just let me touch it up again a little bit for you, because still be external like that, okay? What happens if the wire was at a bit of an angle going through the field, okay? Current is still that way. Now, the problem with this is that we always want the wire and the field to be perpendicular. That's why these hand rules are all about like holding our hands like this, because when things are perpendicular, it maximizes stuff. What happens here is that what we actually have to consider is the components of the current. So we have to consider that it's flowing down and to the left, and it's only this component that really matters to us. When you see the formula that goes along with this, you'll be able to see how we relate that to the calculations. But for now, the big deal is that even though the current's at a bit of an angle, it's still pointing down-ish, and so that's good enough. Okay, that's enough for us to say that when I would do the hand rule, magnetic field pointing that way, current down-ish, still pushing into the board. It's just that in this situation, we wouldn't be maximizing the force. So, what if in the third hand rule, we wanted to show that we have those bar magnets. I tell you that we've laid the wire down like this, and it's current going that way. And I tell you that the direction that it's pushing on the wire in this case is a force coming out to us. I want to know which end of is which, north and south on the magnet. Okay, so for this one, I'm going to start with the current in the wire, and I'm just going to make sure that on my left hand for electron flow current, my thumb is pointing that way for the direction of the current, going that way. But now I'm pushing the wrong direction because I'm pushing into the board and I'm supposed to be pushing out. So I would take my hand and hold it like this so that my palm is now pushing out towards you. That means that my fingers are pointing that way. That means that the magnetic field, the external magnetic field, must be pointing down like that as well. Magnetic fields point from north to south. So that would be the direction it's going. Now this is great if I'm doing wires, okay? But remember, we can also use this third hand rule for just charges even, because really when you have a wire, that's all that's happening is you're giving charges a clean pathway, a roadway to drive along as they're moving. But what I could also do is an example like this. And I'm going to make this, whoops, I'm going to make this one south and this one north. And I'm going to tell you for this one that what I'm doing is taking an alpha particle, which remember is 2 positive, and I'm shooting it up into that field like that. Now, since it's an alpha particle, I'm going to switch to using my right hand because that's going to work for this. And in this one, all the parts basically stay the same. It's just that instead of your thumb being direction of current, it's direction of charge that's moving. Alpha particle, positive charge, moving up like that. My fingertips pointing that way because the magnetic field, the external magnetic field, is going to be pointing north to south. Thumb pointing up, fingers pointing to the left. My palm is pushing out towards you. So in this case, the direction of the force, the magnetic force acting on the particle, is coming out towards you. So as the particle would be traveling up this way, it would get into this area of the field and it would feel itself starting to be pushed out that way. It would curve out towards you a bit. Now that can be shown a little bit better if we change the way that we're drawing the direction of the magnetic field.